What's up, people, and welcome to the ninth part in my introduction to distributed systems tutorial. So in the previous videos we have been talking about all these concepts and modules that we're going to need in order to build these distributed systems that I have demoed for you. And in this actual video I'm going to get to the core point of the whole application where we're going to use all these components and see why also hopefully we need them. So in the application I have implemented almost the all ACK uniform reliable broadcast. I should say immediately that there's like elements of this that aren't implemented. But let's go through the algorithm. It's on page 83 in the book, and it looks like this. So basically it uses a best effort broadcast, which is a broadcast algorithm where you just broadcast all the messages naively to any other node in the topology. We have the P, which is a perfect failure detector, and there is a proof saying that the eventual perfect failure detector, as opposed to the perfect failure detector, the only difference is in performance and not accuracy. So we can assume that this is the perfect failure detector, is the failure detector that we have implemented, which is the eventual perfect failure detector. All right, so in the initialization of the algorithm, this is what you do. You have a set of delivered messages that you set to the empty set. You have a set of pending messages that you set to the empty set. You have a set of processes that are assumed correct that you set to all processes. So all processes are assumed correct as the initialization. And then this is just saying that no messages are acknowledged. All right, so when you get a uniform reliable broadcast request upon event this with this message M, this is what you do. You take the message and then you add it to the set of pending messages. This is the process ID and this is the message. So you set the process to self because you are the one that is doing this broadcast, right? And then you trigger the best effort broadcast with this message. Whenever you receive a best effort broadcast message, you get a deliver from this process with this data. This is what you do. You set the message to the set of acknowledged messages. So now you say that, okay, this message is ACKed by this process P here. And if this message with this sender and this message is not already in the set of pending messages, then you add it to the set of pending messages. And then you do a broadcast. A best effort broadcast with this message. So you relay the message. All right, so upon the event from the failure detector P, you get a crash basically. For this process P has crashed. Then you remove it from the set of correct processes. So if you remember here, we initialized all correct. The set of correct processes was initialized to all processes. So here, this process P is getting removed from that set. You have this helper function, which is can deliver. Basically, can you deliver this message M? And that depends on if it is ACKed by this correct process. Right, so, and then upon exist, this sender and this message, if that is in the pending state, such that you can deliver this message M and it is not already delivered, then you set it to the set of delivered messages, and then you trigger a uniform reliable broadcast deliver of this sender a message. All right, so that might be a bit heavy to start with, but that is how the algorithm works. I suggest you pause the video here and check it out in the book and see if you can figure this out for yourself, what all these parts consist of. Maybe even rewatch the video as I go through it, and it's like so you're like aware of what is going on here. All right, so what does it mean in the actual implementation? So I am not going to consider this the correct set. I'm just going to assume that everybody is correct at this point for simplification. Okay, so let's reuse the message that we had previously here. So we have three processes. Let's ignore the majority part of it to start with, right? So we're saying here that I need acknowledgement from everyone before I deliver. So let's ignore the majority part of it. We need acknowledgement from everyone. So here, Let's open this up so we can zoom in a little bit. All right, so P1 is creating a message here. It is calling at this point the broadcast event. So it is broadcasting to all messages. It's broadcasting to P2, it is broadcasting to P3. It is broadcasting also to itself, not illustrated in the image. So at this point, P1 has one acknowledgement from itself, right? So it cannot deliver the message yet. So P2 here, it receives the message, and if you remember, whenever it receives the deliver, it triggers a broadcast itself, right? So here you get one ACK from P1, and then it sends it acts its own message. So at this point, P2 has two ACKs of this message. P1 has one ACK of the message, and P3 has 0 ACK of the message. All right, so the next thing that happened here is that it broadcast here up to P1. Now P1 has 2 ACK of this message. Here, P2 sends a message to P3. P3 ACKs the message. Now P3 has 1 ACK of the message. And then it receives a message from P1 again. Now it has 2 ACKs of the message. Now it has time to also trigger the broadcasting of the message. So it broadcasts it, and before it broadcasts, it acts its own message. So at this point, P3 receives the last ACK of this particular message, meaning that it can now deliver the application the message. So you can say that, okay, this message is consistent, now you can use it, the application can use it. And then it broadcasts it to P2. Now P2 get the last ACK of this message, because it's like 1, 2, and 3. Now it receives the last one. Now P2 can deliver. And lastly, P1 also receives the ACK of the message, so now it can deliver the message. And as you can see, it needs 3 ACKs before it can deliver the message. So we say that it needs acknowledgements from all the nodes before you can deliver the message to the application. And now I just want to make you think a little bit about what we talked about earlier, like, do we actually need ACK from all the nodes before we can deliver? In this case, do we need 3 ACKs before we can deliver this message? And the answer to that is no. We can use majority. So basically what I'm saying here is that I need, if we have n equals to 5, I need ACK from 3 messages before I can do the deliver. I don't care about these at this point. When I do this write, I can write to 3 nodes. I broadcast all of them, but I deliver when I get ACK from 3 nodes. Because I know that when I do the read, I will also do the read from 3 messages before I deliver the message, the read message in this case. And that means that I will have overlapping quorum, and that means that at least one of the responding nodes will have the last written value. All right. So hopefully you managed to follow along the train of thought. And if you want to take a look at how this looks like, I suggest you open up the broadcast messages here, and then you can see the endpoint here, query, and then the router is routing to the client query function, which is up here. And then you can see that it increments the clock here. And then it creates a transaction of the query that it's doing, and then it's broadcasting this best effort broadcast with this transaction. And then it's doing the broadcast whenever it receives a message. It's also doing the broadcast itself. It responds here to that message because this is a TCP connection. You need to respond. And then you have this on message receive, which I think we should take a look at. So whenever you receive a message, this is pretty interesting. You see here that I increase the acknowledgement counter because I need to keep track of what processes have acknowledged the message, and then I save also the acknowledged messages, and then I do some logging here stuff. And this is very interesting because if I have too few nodes in my cluster, less than 3, I will not be able to have a proper majority quorum because of integer rounding and stuff. So this is a hack in order to get around that. And here I check, this is like, do I have it too small to have a quorum basically? It's a boolean. And this is also a boolean saying that did I get at least one ACK? So keep in mind these two variables. What I do here is I check the ACK counter when I receive a message. Is the ACK counter greater than this? Basically saying that the topology count divided by 2, so like half, and then you seal that with math.seal in order to get it to whole numbers. And or is it a too small quorum and I get at least one ACK, then also deliver, because I want to still be able to deliver the messages even though I don't have quorum if I have too small of a topology. And I mean, what's going on here? What's this here? The number of ACKed messages, is that greater than the topology count divided by 2, and then you seal it? This, if you read in the book, this is the definition you will find in the book. And if you consider what we did here, it is basically, if we check the nodes that we were using, it is this. Like the number of write plus the number of reads needs to be greater than n. And n in this case is the topology count. So that's another way of saying it, basically. And if I haven't already delivered this message, then I set it to the set of delivered messages, basically saying that this is now delivered. And then I check the highest timestamp transaction from these messages. And I see that, okay, you know what, now I deliver the one that had the highest timestamp. And if we take a look at the image, it's this node basically, because this will now have the highest timestamp, because there might be messages that hasn't received it yet. So that is what is going on here. And then I deliver that message. Okay, so at this point I suggest you pause the video and go through it and make sure that it makes sense. Maybe I screwed up somehow with the acknowledgements or whatever. And if you'll be able to find that, I will of course appreciate it. But that is the theory behind it all. And actually that is all for this tutorial series. And I mean, I suggest you read through the book, because that has a lot of good content in it, and it really is a really good introduction to building these kind of peer-to-peer systems. And then what you will need in order to build it properly is topology management and some of the contents that I described here, and then you will be pretty good to go to build some cool stuff, right? So that is actually all for this tutorial series. I hope you enjoyed it. I really enjoyed doing it, and also don't forget to subscribe, and you will find all the material in the description field that you will need. Okay, so thanks you. Bye-bye.